The last correction factor is p-ion, ion recombination correction factor. This factor corrects for lack of collection efficiency. So what is collection efficiency? For an ion chamber to be properly used, we want it to be run at the ionization region. So if we recall this gas amplification curve, we want the chamber to be biased within this region 2, ionization region. Well, this region has a range of energy. So what happens if we bias the chamber at a slightly lower versus a slightly higher voltage? I mean, both voltages allow the chamber to be run within this region. Just one is slightly lower, one is slightly higher. So in theory, because the curve is flat, so the output signal should be the same despite lower versus higher energy, as long as they are in the same region. But in reality, will the output signals to be the same? This essentially reflects the chamber's ability. For example, a good chamber will give very similar output signals despite being run at lower and higher voltages, as long as they are both in the ionization region. This is what p-ion it's all about. So depending on the types of beams, either it being continuous beam like cobalt 60 or pulsed beam like all of our LINAC beams, the equation for p-ion is slightly different. So we only use the equation for pulse beam in our clinic because our LINAC beams are all pulsed beams. In this equation, we bias the chamber at V high, a higher voltage, and we take a reading of the M high from the chamber. Then we repeat, but we bias the chamber at a lower voltage, V low, and then similarly we take a reading from the chamber that is run at V low. And then we use this equation to calculate p-ion. And typically we choose the higher voltage to be 300 volts and the lower voltage to be 150 volts. Let's see some examples. So this is how we calculate the p-ion for a 6 MV photon beam. Because our chamber is calibrated at negative 300 voltage, so in this case our higher voltage is negative 300 voltage and our lower voltage is negative 150 voltage. And we get these two very similar readings, negative 6.06 for the high, negative 6.05 for the low. And then we use this equation and we get our p-ion, which is 1.00110. So which is very close to 1 as we expected, because in theory, for a good chamber, the output signal should be flat. And this is an example for a 6 MeV electron beam. So we do the same thing. We get the p-ion also very close to 1, 1.00755. So you can see they're very close to 1, and they should be. As we said, because 1 is the ideal situation, meaning the chamber is very good, that it is not affected by slightly different biases as long as the chamber is within the ionization region, which is the number 2 region right here. And typically, TG51 recommends using chambers that should have p-ion less than 1.05. And if you look at the p-ion for our chamber value for both electron beam and for photon beams, they are far less than 1.05, and means they are very reliable chambers for the TG51 purpose.